I hope you're having a fun weekend. So today we will be continuing with chapter 12. Previously, in the last lecture, we discussed the curvilinear motion or kinematics of a particle, and then we were talking about the curvilinear motion. First, we were using the rectangular components in order to find our unknowns, for example, velocities and accelerations. We discussed example 12.9 in the last lecture, and today we will be discussing example 12.10. In the 14th edition, it's page 40. Now, the idea is basically the same. You always start by writing your position vector. Now, but sometimes some math is included, some more complicated math is included. So we have to be able to learn some basics in math. Or actually review some of the basics. So today in this question we will have to use both the chain rule and the product rule. Anyways, we will discuss them as we reach there. So in this example, it says that for a short time, the path of the plane in this figure is described by y equals 0.001 x squared in meters. So y is a function of x. Now we have coordinates, right? This is the y-axis, this is the x-axis. And y is a function of x, so that y equals 0.001 x squared. Now we know for a fact, we already knew from the previous example that x is a function of t. Any position is a function of t. X is a function of t. Also, y should be indirectly, or actually directly, a function of time. So, if the plane is rising with a constant upward velocity of 10 meters per second, upward velocity, constant velocity, that means that the velocity in the y direction is known. That upward velocity is 10 meters per second. So this is constant. So the question is asking us to determine the magnitudes of the velocity and acceleration of the plane. So both the velocity and acceleration of this plane when it reaches an altitude of y equals 100. So as it reaches an altitude of y equals 100 meters, what are v as a magnitude and a as a magnitude as well? This is the question. Now, as we've already discussed several times, we have to start with our position vector. You differentiate that once, you get velocity. You differentiate it twice, you get your acceleration. So, start with your position vector. Position vector. The position vector for our airplane here is a function of x and y. Its position in the x direction and the y direction. So it's x, the x component in the y direction plus the y component in the j direction in meters. Now, what kind of information do we have? We only have y as a function of x. That's it. We don't know x. So r basically is x in the y direction plus we substitute this for y. This is 0.001 x squared in the j direction in meters. Now, what do? We need to carry out our differentiation. Now, differentiating this term is easy because we have only x and we know x is a function of t. So if you differentiate that for t, you'd immediately get vx. But here the situation is more complicated, a bit more complicated, not very complicated. Now, here we have this term, this whole thing, we know it's y, right? We just said it's y. Anything in front of j is y, right? And if anything in front of I is x, this is x, and this is y. Now, we cannot directly differentiate y for t. We have to differentiate, we have to carry out something that we call, you already know, it's called the chain rule in math. So the chain rule, what does it say? First, we have y. We know that y is a function of x, but x is also a function of t. So what do we need to do first is we have to differentiate y with respect to x, and then x with respect to y twice. Y with respect to x, and then x with respect to t. So now we need this thing. We need dy over dt to get what? To get vy, right? So as I said, we differentiate y with respect to x, so dy over dx. And then you differentiate x with respect to t, so multiplied by dx over dt. Now, we immediately know that dx over dt is vx, right? So this is vx. The derivative of the position in the x direction is the velocity in the x direction. So this term we already know. Okay, so let's carry out our integration. So now r equals the derivative of this term, this is x, so with respect to t, so this is vx, so it's vx in the I direction, plus, now, what do we do with this term? We have x here, right? Y is a function of x and x is a function of y. So first we have to differentiate dy with respect to x. So differentiate this with respect to x, you'll get 0.001 multiplied by 2x. So this is 0.002x. Right? This is the first part here. And then you have to multiply it by dx over dt, the derivative of x with respect to t, and this is immediately, we know this immediately, it's vx. In the in the j direction, in meters. Oh, sorry, this is not meters, and this is velocity. I apologize. So this is velocity, right? In meters per second. That's it. We're done. So now the question is asking us to determine the magnitude of the velocity. We need to the magnitude of the velocity. So the magnitude is simply equals to the root mean squared of the summation of the squared components. So this is the velocity in the x direction squared plus the velocity in the y direction. Now the velocity in the y direction is this term, everything before the j, this term. So this is 0.002 x px squared. Okay? Alright, so now we carry on. We're not done yet. Now we know that y is a function of x, so that y equals 0.001 x squared, where at y equals 100 meters. The question is asking us to find whatever values at y of 100 meters. So if you substitute this here, you get 100 equals 0.001 x squared, and then as you solve for x, you'll get x equals to 316.2 meters. So this is x, this x. Okay. Now, we also know that the velocity in the y direction is constant and has a value of 10 meters per second. So this is Vy. And we already know that this this whole thing, this whole term, this is Vy, right? This is Vy. So 0.002x Vx is actually Vy. And we know that Vy is 10 meters per second. We already solved for x, so what's left is just Vx. So here we say that Vy equals 10 meters per second, right? And this is also equal to 0.002x Vx, where x equals 316.2 meters. So you solve for Vx and you get a value of 15.81 meters per second. Now you go plug these values Vx and Vy into this equation. So you'll get V, the magnitude of the velocity, equals root mean squared of 15.81 squared plus 10 squared, because this is Vy. So this value would be this value would be 18.7 meters per second. So this is the magnitude of the velocity of that airplane at a height or an altitude of, it's an altitude of 100 meters. Okay, so now this is the easy part. We have another part which is also easy, but it involves not only the chain rule but also the product rule. Okay, so now we're done with the velocity. We need now to work with the acceleration. We know that if we differentiate the velocity, we'll get acceleration. So we go to our velocity equation. So this was A. Let's just start working with B. I'll just choose another color. B. We need to find the acceleration. Again, we start with our equation. The first equation we start with is the velocity equation. Velocity is what? Is equal to the velocity in the x direction, right? The x velocity in the y direction plus the velocity or the velocity in the y direction or in the j direction. So this is what? This is 0.002 x Vx in the j direction, meters per second. It's this equation, right? We start with this equation. Okay, now we need to differentiate that. But look guys, here we have Vx. This is simple. If you differentiate this for time, you get Ax immediately. That's simple. But now here we have this is the y term, right? The Vy, right? This is the whole thing is Vy here. The whole thing is Vy. Now we have two functions or two terms multiplied by each other, and we need to carry out differentiation. So here we have to make use of two things. We have to make use of the one. We have to make use of the product rule, and the chain rule. Both the product rule and the chain rule. Okay, let's see how things go. Now, we need first to work with the product. Let's just discuss the product rule. The product rule says that PR, it's called PR, product rule. What does it say? It says that if we have, for example, two functions, 1 and 2, let's just call them 1 and 2. And we need to find their derivative, the derivative of that part which contains two functions. We need to find the derivative. So the derivative of this one actually equals the first one, or the derivative of the first one, multiplied by the second term, plus the first term multiplied by the derivative of the second term. This is the chain rule. Okay, this is the chain rule. Sorry, this is the product rule. I apologize. This is the product rule, but we also need to make use of the chain rule. Again, the chain rule says that this is, we know this is Vy. We cannot directly integrate Vy into with respect to time because y is a function of x and x is a function of t, and here y is a function of x. So again, we have to carry out the chain rule. The chain rule says that from the here, right? This is the chain rule. dy over dt. So we have to differentiate y for x with respect to x, and then differentiate x with respect to time. So what do we do with this term? Let's just carry out our integration, the whole thing. Now, a prime. Let's just change. So a bar, which is the acceleration as a vector, now is equal to what? Vx. You differentiate that for t. This is simple. This is a x in the I direction. Plus, now comes the relatively complicated part, but not too complicated. Now look, guys, we said if we had two functions or two terms that we need to find their derivative, then we differentiate the first one and multiply by the second one. So if we assume that was our first part, and this is our second part. So we differentiate the first one, but to differentiate this one, we have to carry out the chain rule. So the chain rule says that it's the derivative of the y with respect to x multiplied by x with respect to t. And then we multiply it by the second term. So the derivative of this one is 0 with respect to t, with respect to x. The first one with respect to x is simply 0.002, right? So this is 0.002, right? And then we're not done with this part yet. Then we have to multiply it by its derivative with respect to t, the x derivative with respect to time. So this one, the x derivative with respect to time, dx over dt, is simply what? Dx, position with respect to time. This is velocity in the x direction. Okay? So we're done here. And then we have to multiply it by the second term. So the second term, this is 2, it's Vx. Okay? Add to that. Plus, now we go here. The first term, it's 0.002x, 0.002x, multiplied by the derivative of the second term. The derivative of this second term simply is ax. Okay? So this whole part is ay. Oh, sorry. So this is in the j direction, right? So axi 0.002 vx plus 0.002 x ax in the j direction, and since it's acceleration, so the units are in meters per second squared. Okay, so again, this is the acceleration in the x direction, ax, and this whole thing is the acceleration in the y direction, ay. So this is ax, and this is ay. Okay, now, what are we after? So we're looking for the magnitude of the acceleration. Okay, so the magnitude of the acceleration. What things do we know already? What are the things that we know? Now, I know we've calculated Vx to be 15.81 meters per second. So Vx is known. Now, what else do we know? What else do we know? We know x. We have solved for x. We have just solved for x somewhere here. So this is x, 316. That we know. Okay? What else do we know? What else? So we know almost everything, but we are solving. Now we need to find ax. We need to find ax. Okay. Again, This is AX. We don't know AX. But we know AY. This whole term, we know it. You know why? If you go back to the question, it says that if the plane is rising with a constant upward velocity, so Vy is constant. So the derivative of this is Ay. Ay is now 0 because Vy is constant. Differentiate that for time, you'll get 0. So Ay is 0. So this whole term is 0. So now we get that 0.002 Vx squared plus 0.002 x Ax equals 0. So 0.002 Vx squared, we just solve for Vx. Where's Vx? Vx, 15.81. Yeah, it's just here. 15.81 squared plus 0.002 multiplied by x, which is 316.2, multiplied by Ax equals to 0. So now Ax equals to minus 0.791 meters per second squared. And since we have only acceleration in the x direction, right? Ay is 0. So the resultant should also be in the x direction. Now, if we go back to the airplane here, this is our airplane. So there's the velocity here, which is tangent to the line. Velocity tangent to the line, v. We just calculated v, or the magnitude of v was, magnitude is 18.7 meters per second. And we know that we have an acceleration in this direction because it's minus, so it's going in the negative I direction. Negative I direction. That was A equals 0.791 meters per second squared, and this actually makes sense going in this direction to the inline, to inside, acting inside this curve, So this actually makes sense. Reflect and think. Always reflect and think. So this is correct. But actually, we need actually to find the we need to find the magnitude of the acceleration. We know it's actually the same, but we have to write it down here. Here, the magnitude A equals the root mean square of Ax squared. So this is minus 0.791 squared plus Ay is 0. So this would be 0.791 meters per second squared. And that's it. We're done. Always, guys, please try to practice. As I said, you'll find the product rule and the chain rule in Appendix C at the back of your book. So please practice. There are several examples there on how to practice. You've taken that already in the differential equations, calculus, and several courses as well. So please review that so that you can solve such kind of problems. So that's it for today. Thank you so much.